Which of the two events happened first? It seems like a simple question, but the concept of simultaneity in special relativity is more complex than it seems. Above all, it allows us to understand what is real in our universe. Let's see how. Consider Mark observing, in his reference frame, a train moving with constant speed. Suppose, as an example, that the star is traveling at 60% of the speed of light, corresponding to a gamma value of 5/4. Finally, let's assume that for Mark the train is 24 meters long. Inside the train, positioned in the center, is Andrew. When Andrew and Mark find themselves aligned, two bolts of lightning simultaneously strike the front and back of the train. Let's call A the event, lightning struck the front of the train, and let's call B the event, lightning hit the back of the train. The spacetime coordinates of the two events will be A plus L divided by 2O, and B minus L divided by 2O. Mark knows that the two events are simultaneous as they are equidistant from him, and the light they produce reaches his eyes simultaneously. Similarly, Mark can state that the light from event A reaches Andrew's eyes before the light from event B, as Andrew is moving to the right with the train. Andrew actually sees the light of event A and then that of event B reach his eyes, but his description of what happened is very different. In the train's reference frame, Andrew's position is equidistant from the front and rear of the train. The light of the two events therefore travels the same path also in this reference system. And we must not forget that light has the same speed in all reference systems. So if the light from event A arrives before the light from event B, it is because event A happened first. Events that are simultaneous for Mark are not simultaneous for Andrew. Using Lorentz transformations, we can calculate the spacetime coordinates of the two events in Andrew's reference system. The event locations are xb prime equals minus 15 meters and xa prime equals plus 15 meters. Andrew sees the train as 30 meters long, a longer length than the 24 meters that Mark sees. For the simple fact that Andrew measures the proper length. Due to the phenomenon of length contraction, Mark measures a shorter length. As for timing, Andrew sees the two events happening at different times. First, the lightning occurs in front of the train, then the lightning occurs at the back of the train. Now let's assume that a second train, with the observer Lucas inside, is also passing with equal and opposite velocity in front of Mark. In Lucas' eyes, the light of event B arrives first and then the light of event A. Therefore, repeating the considerations and calculations made in the previous case, we can say that for Lucas event B occurs first and then event A. When Mark sees event A, therefore in his present, the same event is in Andrew's past as it has already happened, and at the same time for Lucas it has not yet happened as it is in his future. In more detail, if events A and B for Mark are simultaneous, Andrew sees event A happen first and event B after, while Lucas sees event B happen first and after event A. The temporal order of events is not preserved. In general, this would seem to undermine one of the most fundamental principles of the description of our reality, the principle of cause and effect. The cause must always occur before the effect. We cannot give up on this. But at the same time we have demonstrated that there are situations in which the temporal order of events can be reversed. For all this to make sense, Starting from the fact that all this is absolutely real in the universe we live in, we must focus on the concept of space-time distance between two events. Two observers measure different distances, different time intervals, and do not necessarily agree on the temporal order between two events. But all observers measure the same space-time distance delta s squared between two events, which in this case is positive. When the space-time distance is positive, it means that there is no cause-effect relationship between the two events, and therefore those two events can happen reversed in time for different observers. Instead, if the space-time distance had been of the light or time type, equal to 0 or negative, then the two events could have been in a cause-effect relationship. Because there could be a signal that starting from event A reaches event B, in this case the Lorentz transformations ensure that all observers see those two events in the same temporal order. First the cause, then the effect.